This leads to our second reason for replicating. Our first reason for replication was to confirm the consistency of our findings. Do the findings hold up over repeated tests? But the second reason has to do with generalizability, or so-called external validity. Do the findings hold over participant characteristics, places, time, culture, and context? Generalizability also asks if the findings hold over the research histories of participants. Are those with prior exposure to research equally responsive to our treatment as those who are seeing material for the first time? And does whether and how much we pay our participants affect the generalizability of the findings to the real world? If we measured factors predicting urban anxiety in New York in the 1920s or today, would we expect similar factors? How much can we generalize old findings to current times? If I'm investigating a teaching method in the classroom, does it matter if the work done was done in the classroom at the left, which looks a lot like most classrooms today? Does it matter if I'm actually teaching in the classroom in the right? Often, our studies will give questionnaires in a waiting room, with IRB approval, of course. If you administer the questionnaire in the waiting room on the right, does it generalize to patients in the waiting room on the left? The broader framework for understanding this concern is what Cattell called selection. To illustrate the point, he argued that every datum we collect is a selection. One dimension of selection is person. In the population of possible persons, our sample is always a selection from the broader population, so our sample results generalize to that population only if our sample is a good representation of that population. But that's not all. Our measurement batteries are selections. Why do we give this measure of depression instead of that one? Why do we give this memory measure rather than that one? So our results are also only generalizable to the population of memory and depression measured to the extent that they're good representatives of the memory and depression constructs. And though we seldom think of it, the Times Square example reminds us that occasions of measurement are also selections. Measuring you in 1924 does not necessarily represent measuring you or others like you in 2014. Cattell's data box was conceptual, but it sensitizes us to the fact that everything in our study is a selection: participants, measures, and occasions, but also experimenters, research staff, settings, and geographic environment. Each of those selections constrain the generalizability of our findings, and that is inevitable. But where it is problematic is if we're not aware of the constraints on our generalizability, and if we overgeneralize, making more of the universality of our findings than is really there. Just as psychology has made an increased move toward replication, NIH is making serious moves to promote both reproducibility, in other words, the ability to replicate, but also rigor, which really means experimental quality and control, ruling out alternative explanations, and improving internal validity. Grant writers and reviewers received new guidelines in 2016, which continuously evolve to support enhanced rigor and reproducibility. NIH has laid out 4 different areas that grant writers must address to improve the quality of science. Notice that if number 1 means report prior literature, no more can spotless minds simply assert that little is known. Number 2 talks about justifying research design. A lot of the rest of this week is aimed at boosting number 2. Number 3 is a little misleading. It really is a generalizability demand. In particular, number 3 emphasizes that all work should try to be generalizable to both men and women, and should study differences in response by men and women. And number 4 is what we might think of as reliability, making sure that the biological agents, biomarker tests, assays, and so forth, are of high quality and are measuring what they claim to be measuring. NIH is providing specific details all throughout the standard grant application where rigor and reproducibility are specifically to be addressed. And NIH grant reviewers are being told to comment on rigor and reproducibility and to let attention to these issues influence their scores. By making internal and external validity matter in terms of grant dollars, the coin of the realm for the American academic, there is a real chance that this initiative can make a difference. At the core of this move towards rigor and transparency is what's being called the open science movement. NIH also tries to codify this through what they call mandatory data sharing rules, especially for clinical data. In open science, and think about this, you publish your questionnaires. You make your de-identified data available to others after you're done and hopefully have published quickly. You publish in free open access journals. You publish your research protocols and intervention manuals in open source areas. Open peer review is interesting. I've done it a few times now. Rather than reviewers of your work commenting confidentially to you and the editor, the reviewer comments and your responses are published along with your final published article. This makes transparent what changed and what others thought about your work. Under some circumstances, this counts as another publication, another coin of the realm for the reviewers, which further incentivizes them to do the review. I should briefly note that a topic we won't spend much time on in this class is meta-analysis, but that's another way of trying to approach big picture replication in a systematic way. Meta-analysis is a statistical technique for combining findings from independent studies. For example, if you're looking for the effectiveness of, say, the Atkins diet versus Weight Watchers versus paleo, a meta-analysis will combine the results of many Atkins, Weight Watchers, and paleo studies after grading them for quality and rigor. The meta-analysis gives us a bigger picture of what really holds across multiple replications and, we believe, gets us closer to the truth. Here is a meta-analysis of a study. In the left column, you see 6 different studies listed, and without going into details, not only are the individual replications all displayed, but then at the bottom, there is an overall summary of what holds across studies.